Hi, so this is Jack from the PyTorch X-ray team. Today, I want to do a follow-up of my previous video, which is how to debug PyTorch X-ray. In that video, I briefly go over how to capture a profile and how to interpret a profile. Today, I want to expand on that topic and go into more detail on how to add annotation, how to interpret the model forward, and how to map the fusion op like in the profile back to the actual computation in your model. So let's get started. All right, I need to reconnect. We just close this windows. All right. So my setup is similar to the last time. I am using the PyTorch X-Ray nightly. You can use the 2.3 release or the 2.4 release will be out very soon, which will cover all of the feature I used today. So if you haven't watched my last video, I strongly recommend you to do so. Um, but TLDR, you can install the nightly wheel using the link here, then install the libTPU, or you can just install the release version following our README. Okay, let's just very quickly do a sanity check. It's always good to check what we have. Torch 3, Torch version. Yeah, like I said, it's nightly. Okay, everything seems fine. So today, all of my plan is to talk about the profile. I do plan to first show you how to dump HLO, and then from the HLO graph, we can know like what does the annotation actually appear and why it looks the way it is like in the profile. So here is the training trend decoder only base that I showed you guys last time. Pretty much like this is the file that is doing the decoder only model, which I simplify from the llama model. I think there's no KV cache, no lottery embedding, there's no attention mask. But other than that, it's a pretty traditional like the decoder only model. And I don't think that's anything X-ray specific in this file. So let's just run this model. I might need to make some change. I think currently it will run for how many steps? I think 300. Let's reduce it to 100 to make it finish faster. And then I'm going to use the environment variable to dump the HLO graph. I'll show you quickly. Let me measure this. I don't remember all of the flags, but yeah, this is what I want. So it's X-ray flag equal to dash dash X-ray dump to, and then like this is directory I want to dump to. It's good for me to make sure that directory is empty first. Okay, it's not great. Okay, now I think we are ready. Examples chain decoder only base. It should start running fairly quickly. This is a very simple model. Like I think my default config, let's see, 4-layer. Okay. Actually, let's do one thing. I think I mess up my local config a bit. Yes. So let's start from a fresh. Status. Yeah, I have some local change. Let me check out all of them so it's easier. So let's set the step to 100 and then restart. Yeah, I realized one thing, it might already save some HLO, but it's okay. Like for the purpose of this video, it should be okay. Let's just quickly chat cd x-ray dump. Okay, there's nothing there. Oh, I forgot to include an environment variable. That's what happens when you doing a coding live. Let's try again. All right. Great. You can see there are a lot of stuff being dumped here. So what we are going to look at right now is the before optimization.txt. So this is the HLO that we construct in the PyTorch XLA, and this is what we pass to the compiler. And then you can also see a bunch of after optimization, like those are the HLO that actually being run on the device. Well, they first got lowered to LOO, but so let's see. There are two graphs, and one of them is actually because we use fake data. One of them was materializing was fake data. Let's look at this one. So I think this one is a real one. Yes, this one is the decoder only models HLO. So you will see it's very difficult to see what's happening here. There are some reshape, transpose, there's a dot which is matmol, but still it's very confusing. It's very difficult for you to see what exactly happened here. So which is why like we want to turn on something called X-ray IR debug equal to 1 and X-ray HLO debug equal to 1. So let's remove everything here. With these two flags, like let's run it again and see how the HLO will be different. All right, started. All right. Let's see. I believe this one will be the tensor materialization, but let's see. Yeah, I think this one was the answer. Let's try to look at the actual model. See this one. It's difficult for me to see which one is which. Let's try this one. Yeah, this one is a real one. Okay, how do I tell? Let's see. Like in here, right now, like in each HLO, besides the HLO itself, it also contains metadata. The metadata by default, it contains a couple things. It contains like which op it is. For example, like this constant is from the NLL loss backward. And the op name it's the NLL loss. Let's find something else. Here's A10 view. And then it also tell you which line is coming from. It's in the torch module linear.py, so it's part of a linear reshape. It's following by dot, so it makes sense. So by not doing anything, just run your model with XYIR debug and actual HLO debug equal to 1, like you already carry some very useful information. But that might not be enough for us. Like for example, there are many linear layers like in a feed forward. It's difficult to see which one is which. Can we do better? Actually we can. So let's do this. So right now this decoder only model, there's nothing PyTorch XLA specific in it, but we can add some profile annotation and let me show you. I can never remember the actual API, so what I usually do, I go to the debug, RESTnet profile.py. We want to import this. And then let me add some annotation to the function. For example, here, speed typo trace me. So this is a decorator. Okay, so this one is IMS known. Let's see. This one is attention. So let's say attention dot forward. This is MLP. Let's do the same thing. This one is a decoder layer. decoder layer. This one is the model. Okay, now let's remove everything in this file. And let's run the model again and see how the HLO will be different. One thing to keep in mind is, like, in order to reduce the compilation time, we usually use something called persistent cache, which will cache your X-ray compilation like into your local disk. However, like if you actually modifying the metadata like what I do, just adding this like the tracing annotation, you probably don't want to use the persistent cache because this metadata doesn't change the compilation hash, which means it will not recompile, and wherever HLO you generated, it will not have the new sharding annotation. Not sharding, the debug annotation. Okay. Still the same problem. I don't know which one is which one. But let's see. Add and apply. Okay, this is optimizer. So this one is what we look. So let's look at the annotation we just added. Model.forward, but let's look for MLP. Okay. It's not showing up. What do I do? Okay, so this one is might not be the one I want. Let's try this one. Okay, 1 second. This graph before. Graph MLP the forward. It doesn't show up. Well, it's a good exercise. Oh, it's a decorator. I should have noticed. Speed of tracement. Let's try again. Oh, I guess you know what not to do next time. All right. Hopefully this will work this time. Okay, great. Now I can see it. Let's find the. Okay, now let's see. It's still a same reshape op on top of the op type and the op name. Well, it's actually in the op name. It depend a bunch of other information. For example, this one, it tell you like this reshape is coming from the model.forward, decoder.forward, MLP.forward, and it's a view op. So it tell you a sequence of the event happen, and like now you know exactly where to find the MLP and where to find the attention, for example. It will be more clear, like in when we look at a profile. And now let's look at a profile. But before we do so, I do plan to add a few more annotation. I will show you how and why. So if you remember, here is, so let's first do one thing. Let's only do the inference for now. Let's do line comment. Okay, so now we're only doing the inference, and then I want something called step trace. Step. I will show you why I want this. Okay, what else do I want to change? That should be it. Okay, now similarly, we need to collect a profile. What I do is usually just copy paste my own code. Example, debug, search and ResNet profile. So we need to copy this boilerplate code, which Ideally, we should just make a single function, which remind me that might be a good idea. All right, let's put it here. I need the OS. Okay, look, it's going to save in the profile log there, which is temp.profile. Do I have anything here? ls. Okay, I already have something. Let's just remove it. Okay, now let's rerun the model. We don't need to see the HLO dump anymore. So let's remove this X-ray flag. And now if we start tracing, actually, let me do one thing. Okay, it's fine. Never mind. Like I explained last time, it's actually not a good idea to start the tracing ahead of time because it will also trace the compilation. It's usually a better idea, like in a training code, in here you specify, for example, if step was equal to 5, which usually means compilation already happened, then we start the tracing. This is usually fine for smaller model, but for longer model, compilation sometimes take like minutes. Then it's not a good idea to let the tracer start ahead of time. Okay, now it's finished. Why is it taking so long? Let's verify whether the trace is there. cd file. Okay, it's definitely there. Now let's open the TensorBoard. Like I said, I never remember these commands. Okay, if you didn't watch my last video, you need to install the TensorFlow CPU and the TensorBoard plugin, and then you can just, if you like me use VS Code, you can directly just open it up on your local host. Otherwise, like you need to set up the port forwarding from your TPU to your local machine. Okay, that's only one. Let's go to Trace Viewer. All right, that's pretty beautiful. Like I explained last time, like these two, they are corresponding to the device execution, and down below is everything that's happened on the host. On the host, there's something very interesting here. Like you see in here, it says step 0. And if you zoom in a lot, you see like they are actually like step 1, step 2, step 3, 4, 5, 9. So this is what's added for the step trace we have. What do I do? Oh, never mind. It's in here. So we have a step trace in here. So then in every step, it's going to increment the step here, and it's going to annotate, add the corresponding annotation to the HLO. This way, it's easier for us to see which step we are tracing. Another thing I want to quickly point out is like you usually notice tracing is a lot quicker than the device execution. For example, in here, tracing takes 4.28 milliseconds. A single device execution takes 33 milliseconds. This is a good thing, generally speaking. This means like your tracing is not like your model is not tracing bound. But then what exactly is happening? Like why am I keep tracing while the device hasn't finished execution? That's because like in PyTorch XLA we use PGRT runtime, which has a feature for us to schedule the asynchronous execution. So in the Python main thread, we will just keep tracing, which is keep running a PyTorch Python code, and then we queue up a bunch of execution to the backend, to the compiler, and the TPU. And they shouldn't be blocking. Like let's limit, I think somewhere around 24 to 36. Like let's limit how many graph you can accumulate. But until you reach the limit, pretty much you can keep queuing the graph, unless you are actually want the result right away, which is usually meaning that, for example, you're trying to print a loss. Well, if you want to print a loss, you have to wait until that graph execution to finish, which is actually what happened in our case in every 10 step. If you look at our code, like we have this, like in every 10 step, we are trying to actually print the loss. So which is what happened like in every 10 step, like you see this, that's a blocking transfer from device, which was transfer the loss from the device. And then it becomes a blocking operation, which is why it takes so long. All right. So this is a tracing. So you see in here, like tracing happen in the main thread, then you see like in every 10 step, that's one step, that's really slow. And let's go back and well, actually there's one more thing I want to show you. If you zoom in a bit, you something very interesting. So all of these are the annotation we just added. Let's see if you see the decoder dot forward, which is the trace me we had the decorator we add in the decoder layer forward. It's similar to other. So in here, pretty much it was telling you like which layer that the Python main thread is actually tracing. Well, it's one thing interesting. You see the attention forward tracing takes a lot longer because attention itself, like the logic, is more complicated. If you look at here, than the MLP. MLP is pretty much just like 2 to 3 linear layer. So tracing the attention is more expensive than the tracing the MLP layer. But executing the MLP layer is usually more expensive because the parameter is larger. Now let's actually look at the device. See, so in my own code, like the config is like it's a 2-layer, like a decoder only model, which is means in every single execution, like there are 2 decoder forward, which was match your expectation. And in each decoder layer, there is a attention dot forward, and then let's say MLP dot forward, which also kind of match your expectation. There are also IMS known, I believe, very small. Yeah, it's in here. Like computation-wise, like you see, even attention is like very small compared to a feed forward. It also has to do with my parameter choice. My intermediate size was 64 times 1024. 1024 was the hidden size. So like the MLP layer is a lot more expensive than the attention layer. But more interestingly, if you look at here, so here is the TensorFlow name scope, which is all of the annotation we attach to the HLO, which reflected in the TensorBoard. And then above is actually the XLA op that actually got executed. Let's see if we can make sense of them. See, like here there are a lot of different op. There's a bunch of fusion. How is it possible I ever figure out like which fusion corresponding to which op? Well, attention is a bit difficult, but let's actually look at MLP, which will be a lot more obvious. Let's see. So in MLP, oops, here, you see it's pretty much there are 2 fusion. The fusion 19 and fusion 60. So let's revisit what MLP does. MLP dot forward. Well, it was up projection, which is a linear activation function, gate projection, which is also a linear, down projection is linear. So pretty much it's 3 linear module. And it's the batch size, sequence length, hidden dimension to the batch size, sequence length, and the intermediate dimension. Now let's see. In the first fusion, what we see is the output. Well, here's how you read HLO. So the first part is the output. So the fusion.19 is the name of this op, and it has an output shape of F32, which is type, and the 16 by 512 by the 6. I believe this is the intermediate size, and it has 2 input. Well, a couple input actually. It's a convolution fusion. The convolution fusion, like I said last time, is usually means it's a matmul. I can tell you, like it's in the model forward, decoder forward, MLP forward, and it's a matmul. So kind of spoiler alert. All right, then how do I know which one it is? Well, the output size is 16, 512. Now let's going back and let's figure out like what's our batch size. It's in here. So our batch size is 16. Our sequence length is 512. That's what we define. And our hidden dimension, like I said, our hidden dimension is the 1024 and intermediate dimension is 64 by 124, which I actually don't know how much it is. Okay, it's the 65,000 something something. Well, that's actually already a good hint. So what this means? This means like the input shape should be the 16 by 512 to the 1024 to the 16 512 by what's the number? 65. So this is the input shape and output shape up projection. Now let's look at our profile. This profile's output shape is 16512 by the 65,000, which is fusion 19, which pretty much indicates this one is the up projection. Is this one or it's the gate projection? But gate projection also have activation function. Okay, how can we be sure? Well, we can actually just look at this op. This op is called fusion.19. Let's go to the graph viewer. The op name is fusion.19 and search graph. Oh, it doesn't show me anything. That's a bit annoying. That was unexpected. But then I guess at least from the what I just told you, from the annotation, and the like input shape and output shape, you can already kind of guess like what this one is. And I guess the fusion.60 was the output shape. 16 by 512. Is this one the end of the MLP? Yes, the end of MLP4 ends here. Yeah, the fusion 16 is the end of MLP. So I guess this one is the output of MLP, which is BSH, which is kind of weird. It should be the 16512 by 1024. I probably need to look into what happened here. But if that was not enough hint, for example, for the MLP itself is relatively straightforward, because like, there's only 3 memo. What if I want to figure out what's happening in the attention.forward? Oh, well, it's easy. You can actually just add more annotation. Like for example, let me quickly show you. In here, you can add xp.trace_me. xp.trace_me. I think it's called trace me. I should have known the API better. Actually, let me just look up debug. It's in the Torch X-ray debug profiler.py. Yeah, it's called trace. It's the capital trace one. It's the one I want, I believe. xp.trace, and this one was the QKV projection. Well, this does is similar to a step trace. Pretty much, you will you should only use step trace like in the outermost, because step trace is actually going to call touchxp.sync or mark step for you, and you also increment the step number. For the regular tracing, you should use xp.trace. This one just reshape the QKV reshape. Well, I also have a flash attention version, which you probably don't really care. See here. Here is the QK computation. Then here is the softmax. You get the idea. I'm probably not going to finish like all of this, but we can just run it once and see whether that makes things any clear. Let me first just remove the existing profile so we don't get confused which one is which one. And let me just run it again. Remember, you always want to run with X-ray IR debug equal to 1, X-ray HLO debug equal to 1. Otherwise, you wouldn't see all of this annotation. They will make the tracing slightly slower, but it generally doesn't really matter in real life. Okay, it finish. Again, I want to remind you, like I just commented out the backward part. So all of the trace we look at right now, they are actually forward only. But backward, they are similar. With the only problem is that you cannot actually annotate anything in the backward because backward actually happens in the C++ for the PyTorch. But you can annotate the optimizer if you want to. Okay, now let's look at the profile. All right, let's see. Loading, loading. Okay. Yay is here. So now like it's even better. Now remember we used to only have attention.forward and we have MLP.forward. Now with the annotation we just added, now we actually know, like for example, this fusion actually corresponding to QKV projection. 16 by 4. This one is ratio. So this is the sequence length, like this is 6. This is a non-KV head, I believe, and this is the head dimension. So it kind of makes sense. All right, where were we? Yeah, this QKV projection is also QKV projection. And then here's the QK, like the memo of the Q and K transpose, which was iron sound like in my implementation. And the QKV projection. This one is probably V projection. And then it was the reshape. So you get the idea that you can add more annotation to your Python PyTorch code to make it clear. Like for example, if you're ever curious, like how long does the QK takes compared to like the QKV, like the final, and how long does the output projection actually takes, which is difficult to see from the profile itself because all of them shows as fusion. But with this annotation, you can actually make it very clear. So which part of your model actually takes longer to execute and which part takes longer to trace, which if you remember, which we can take a look again in our tracing part. Attention is actually takes longer to trace, but MLP is actually very cheap to trace built on its layer, but MLP is a lot more expensive to execute. So those are the insights you can get. Yeah, I think that's everything I want to talk about for like this tutorial. So to recap, I show you how to dump the HLO for your program. I'll show you how to add the tracing annotation and how will those tracing annotation show up in the profile and how to interpret those tracing annotation. So I hope this tutorial is helpful. If you have any other question, feel free to leave a comment or just open GitHub issue on PyTorch X-ray GitHub repo. So thanks for watching. Looking forward to see you next time. Hi, sorry. I just want to continue on a very quick topic on how to actually visualize the fusion. So if you remember that we were talking about in MLP forward, there were actually two fusion, the fusion 14 and fusion 58. So what you can do is, like I said, in the tools, you can select a graph viewer, then you can type in the op name. Like in our case, let's look at the first fusion of the MLP layer, which is a fusion.14. And graph width is like how long you want to view it. So if you recall, like fusion.14 is actually the matmul, the first linear layer, like in our decoder model. Let's see. we suspect is this one, and the input is 16, which is a batch size, sequence length, and the hidden dimension with 1024, and the output, the last dimension should be the intermediate dimension, which is 65,000. So if you look at what happened here, like in this fusion, it takes two inputs. The one is 6 by 15, or it's actually take more than two. This one was broadcast, but you see here parameter 0. Let me zoom in. So 16 by 512 and 1024, this is the batch size, sequence length, hidden dimension. Pretty much this means this is the input to the MLP layer, and then it goes to multiply and convolution fusion. And here the 16, 512, 1024, well, here's the part that's a bit difficult to visualize, which is because like the memo will always become a convolution fusion and the input shape might be slightly weird. But what matters is the output shape is 16 by 512 to the 65,000. So this is the output shape, if you remember, of the up projection, which is why I think like this fusion actually represents the up projection. Then if you see like the output, the convolution 17, which is this graph, it becomes the input of another fusion, which is here. I suspect this one was the gate projection. Yes, the temporal. This one is probably the gate projection because it was multiplied. And then eventually, like there's another convolution fusion. The output shape is 16 by 512 by 1024, which if you look at again, like this is the down projection because like the up projection times the gate projection, and then it goes to the down projection, which is a linear layer, which with the intermediate size as input feature, output feature is hidden size, and hidden size is 1024, which 16 by 512 and 1024, which batch size, sequence, and hidden size. So this is the output. So we can conclude this convolution was the down projection. So this is kind of end-to-end. So pretty much like in here with annotation, you can look at which fusion corresponding to which layer. Then in this op profile with the op name, you can kind of infer like what exactly layer, what exactly is this fusion doing? Like the whole convolution fusion might be a bit confusing, but with the input shape and output shape, you should still be able to figure out what it's actually doing. So yeah, that's the only thing I want to add. Thanks.